Let's look at stability for Chief Mate's MCA examination, July 2016, question number 2. It says a vessel in salt water is heeled 3.9 degrees to port and has the following particulars in salt water. Displacement 13,200 tons, kg 8.23 meters. All the ballast tanks are initially empty. Using the stability data booklet, calculate each of the following. A. The weight of saltwater ballast to load into number 2 dB tank starboard to bring the vessel upright. Part B. The angle of heel after bringing the vessel upright using the saltwater ballast in question 2A and then loading the following. 32 tons container kg 7.6 meters and transverse center of gravity 2.88 meters to port. 28 tons container kg 8.66 meters and TCG of 3.44 meters to starboard. 26 tons of container kg 4.63 meters and TCG of 6.42 meters to port. Use kg of tank for kg of water ballast. Part C. The distance of the center line TCG to load a heavy unit of 58 tons so as to bring the vessel to a final upright condition. We'll first calculate the km at 13,200 tons. This we have obtained from the hydrostatic data as 8.41 meters. The kg of the question, which was given as 8.230 meters. We will take kg off from the km and we'll get gm at 13,200 tons as 0.180 meters. We'll use the formula tan of initial list equals to ggh divided by gm initial. So when we put in the values, we'll put tan of 3.9 degrees because 3.9 degrees was the value which was given in the question as initial list, which was on the port side, equals to ggh over 0.180 meters. So this is the gm and this is coming from this place. So we obtain a ggh value of 0.0123 meters to port. The direction is very important, which is port, which is my ggh initial. Now MCA recommends to take the ggh to 4 places of decimal, but if you are taking it to 3 places of decimal, that is also acceptable. Now initial listing moments is equals to the ggh initial times the displacement initial. So that will give me the moments. So initial listing moments will give me 0.0123 meters, which was my ggh initial, which I had obtained from this place, times the displacement initial, which is 13,200 tons, which was given in the question. So initial listing moments has been obtained as 162.4 tons meter and the direction is port. Now in order to bring the ship to upright, my port listing moments shall always be equals to starboard listing moments. When these moments are equal, that means my ship will be upright. So port listing moments, we have already calculated it as 162.4 tons, which has come from this place. And starboard listing moments will be equals to W times the distance, because moments is nothing but the W times a distance. So we'll write it as 162.4 equals to W, which we need to find it out, times the distance, which is the 6.48 meters, which is the distance of the number 2 dB tank starboard, the transverse distance from center line of number 2 dB tank starboard, which has been obtained from ship particulars. When we solve for W, we will get W is equals to 25.1 tons, which is equals to the weight which we need to load in number 2 DB tank starboard in order to bring the ship upright. So this is the answer to the A part. So weight of ballast to load in number 2 DB starboard tank is equals to 25.1 tons. Now to calculate the B part, we'll make a kg table which have the columns as description, the weight in tons, the kg in meters, and vertical movements in tons meter. We'll make our initial entry, which is the initial weight of the vessel, which is 13,200 tons, and kg of the vessel, which is 8.23 meters. So we get the vertical movements, which we get it as multiplying by weight times the kg. Now, number 2 DB tank starboard was loaded with 25.1 tons, which we have got it from here. And the kg of the tank from the hydrostatic data has been obtained at 0.60 meters. So the vertical moments we have got is as 15.1 tons meter. Again, this has been obtained by multiplying these two values. Now, since these tanks were initially empty, when we have loaded this amount of water inside the tank, it gives free surface moment. So we need to add the free surface moment which has been induced because of number 2 DB tank starboard side. So there is no weight with respect to free surface moment, there is no kg. So the free surface moment which has been given in the hydrostatic data for the number 2 DB starboard tank is 680, which is for the fresh water. So we need to convert it to salt water. So we will multiply it with the density of the liquid inside the tank. In this case, it was the salt water, which is density as 1.025. So we'll write it as 680 multiplied by 1.025. We have loaded a container which weighs 32 tons at kg 7.6 meters, and we have got its associated vertical moments by multiplying these values. Another container was loaded weighing 28 tons, which was loaded at kg 8.66 meters. So associated vertical moments have been obtained by multiplying these two values. The third container weighing 26 tons was loaded at kg 4.63 meters, and its associated vertical moments is 120.4, which has been obtained by multiplying these two values. We will add up all these values to get the total weight, which we'll get as 13311.1 tons, and we'll add up all these vertical moments to get the total vertical moments, which is 109954.2. kg final would be sum of all vertical moments divided by sum of all weights. When we put in the values, we'll get 109954.2, which has come from here, and divided by the total weight, which is 13311.1 tons, which has come from here. So we got a kg final as 8.260 meters. Now we will calculate km final at the displacement of 13311.1 tons by looking into the hydrostatic data and by doing the interpolation. So we have obtained the km as 8.400 meters. The kg final has been obtained as 8.260 meters, which has come from this place. When we take kg off from km, what we'll get is the gm final. So the gm final, what we have got is 0.140 meters. Earlier we had made a table for the vertical moments. Now we'll make a table for the horizontal moments, which is this one. So the table consists of the following columns. Number 1, description. Second is the weight in tons. Third, TCG in meters, which is transverse center of gravity. The moments, which has further been divided into port moments and the starboard moments. So the initial weight was 13,200 tons, and the initial GGH was 0.0123 meters, which was towards port. This we had calculated in the very beginning at this place. We have got its associated moments as 162.4, which is by multiplying these two values. Since the TCG was port, we have to put the moments in port. Now, number 2 dB starboard tank was loaded with 25.1 tons, which we have got the value from this part. And the TCG of the number 2 dB starboard tank has been obtained from the hydrostatic data as 6.48 meters towards starboard. So this associated free surface moment, its associated horizontal moments, we'll write it as 162.4. The container was loaded, the first one weighing 32 tons, and it was loaded at 2.88 meters to the port side. So we have got its associated horizontal moments as 92.2. Second container was loaded as weighing 28 tons, and its transverse center of gravity was 3.44 meters starboard. So we have the moments on the starboard side. The third container was loaded weighing 26 tons, which was loaded at 6.42 meters on the port side. So we have its associated horizontal moments, which is 166.9 on the port side. We'll sum up all the weight in this column, which we'll get it as 13311.1 tons, which is same as this value. And we'll sum up the port moments and the starboard moments. So when we do it for port moments, we'll sum up all the values which are in the column of port moments, which we get it as 421.5. And when calculating for starboard side, we'll sum up all the values which were on the starboard side, which we have got it as 258.7. The next step is to calculate the effective horizontal moments. So this means that what is the moments actually acting on board the ship. So in this case, it would be this value which needs to be taken off from this value. So this is 421.5 minus 258.7, which means this is the resultant moments which is acting on board the ship, which is 162.8 tons meter, and it is acting in the port direction. This is the resultant value, I say again. Now, when we calculate the GGH final, we'll say its sum of effective moments divided by the sum of displacement. So the effective moment was 162.8, which has come from here, divided by the total displacement, which is 13311.1 tons, which has come from here, which has given up the value of 0.0122 meters in the direction of port. So direction is important. We have calculated GGH to 4 places of decimal because MCA recommends it to take it to 4 places of decimal when we deal it with GGH. But if you take it to 3 places of decimal, it is also acceptable. When we put the formula, tan of list is equals to GGH final divided by GM final, we'll put in the values for GGH final, which is 0.0122 meters, which we have obtained from here, and divided by GM of 0.140 meters, which we had calculated before, which is here. We get a final list of 5 degrees to port. The direction is important because we had the listing moments to the port side and the listing lever was also port side, so the final list will also be towards port. So this is our final answer for part B. Now when we look at part C, it says the distance of the center line to load a heavy unit of 58 tons so as to bring the vessel to a final upright condition. Again, to bring vessel upright, port moments needs to be equals to the starboard moments. We know our port listing moments, which was 162.8, which has come from here. Once we counteract this moment, we will be able to bring our ship in an upright way. So 162.8 will be equals to the starboard moment, because that's the moment we require on the starboard side to bring the ship upright. So moments is nothing but W times some distance. So 162.8 is equals to the weight of the object was known, which was 58 tons. It was given in the question, and distance is what we need to find out. When we solve for D and bring this 58 down here in the denominator, we'll get 2.807 meters, and this needs to be on the starboard side. Again, the direction is important, because our initial listing moments was on port side, so we need to load it on the starboard side to bring the ship upright. So our final answer to part C would be distance at which weight should be loaded is equals to 2.807 meters on the starboard side.